Okay, greetings to all. This is Dr. M. Shakti Mohan, Associate Professor. So today we are going to discuss about the content called logic gates. So in that we are going to discuss about the design and its implementation of logic gates. So this video is under the playlist of digital electronic circuits. So we'll discuss one by one. So basically, what is logic gates means? So if you want to build the combinational logic circuits means, so those are the building blocks, right? So that is with the help of logic gates only we are going to build the combinational logic circuits. So generally, what is combinational logic circuit now? So without a memory element, so with the help of logic gates we will implement some function means, that is what combinational logic circuit we'll discuss one by one. Okay, so I hope you can see the screen. In this video, we are going to discuss about the implementation of Boolean function using logic gates. Also, to discuss about the logic gates, right? Okay, so the first point, logic gates are mainly used to construct the digital systems. Okay, so digital system in the sense both combinational logic circuit as well as sequential logic circuit. So those are that is the logic gates are the building blocks of all the kind of circuits, right? Okay, so the types of logic gates are AND gate, OR gate, NOT gate, NAND gate, NOR gate, EXOR gate, and EXNOR gate. Okay, so for each and every gate will be used for performing one kind of operation. We'll discuss one by one, right? Okay, so first we are going to discuss about the AND gate. So if you want to perform the multiplication operation, right? So for example, y is equal to a into b. Okay, so this kind of multiplication operation is performed with the help of AND gate, right? Okay, so you can see this is what the structure of the AND gate. So there are two input, that is a and b, and the output is y. So the output y is equal to a into b, right? And the IC number for the AND gate is 7408, right? Generally, it is known by 74LS08. Technically, we can call it as 7408 IC. And this is what the truth table for the AND gate, right? So A and B are the input. So since it is a 2-bit, so with the help of 2-1 concept, we just make the input, that is 0, 0, 0, 1, 1, 0, and 1, 1. And the output is Y. Okay. So as we know, y is equal to a into b, right? So that means with the help of the multiplication, we'll derive the inputs, right? So 0 into 0 means output is 0, 0 into 1 means output 0, and 1 into 0 means output 0, and 1 into 1 means output 1, right? So this is how the AND gate is implemented. So next we are going to discuss about the OR gate. Uh, okay, so you can see the logic diagram for the OR gate. So this is what the structure for the OR gate. Here, what is the operation will be performed in the OR gate now? That is y is equal to, sorry, y is equal to a plus b. That is logical addition operation will be performed with the help of OR gate, right? Okay, so a and b are the inputs, and the output y is equal to a plus b. And this is what the truth table for that. So that is 0 plus 0 is equal to 0, 0 plus 1 is equal to 1, and 1 plus 1, 1 plus 0 is equal to 1, and 1 plus 1 is equal to 1. Okay, don't forget here 1 plus 1 is not 10 like binary addition. Since it is a logical OR operation, the 1 plus 1 is equal to 1 only, not 10. Okay, so please remember that, right? Okay, so the next gate is the NOT gate, that is inverter gate. So before that, the IC number for the OR gate is 7432, right? Okay, so the next gate is NOT gate. That is, if you want to perform the negation or inversion operation with the help of NOT gate, we can do it. That is, the input is A means the output Y is equal to A bar. Okay, if you provide 0 now, it will give 1. And if you provide 1 now, it will give 0. That is what NOT gate. Okay, you can see this is what the structure, that is logical structure. And this is what the truth table. That is 0 now, it will produce 1. And 1 now, it will produce 0. Right? Okay. So the next logic gate is NAND gate. Actually, the IC number for the NOT gate is 7404. Okay, so please remember that also. And the next gate is NAND gate, NAND gate. Actually, it is the combination of AND plus NOT gate. That is what NAND gate. Okay, you can see So the AND gate structure will be there, and from the NOT gate there will be a bubble, so that bubble will be there here, right? So that means it will perform the opposite operation of AND gate. That is y is equal to a into b the whole bar. That is what the operation of NAND gate. So here I am just mentioning the truth table for the NAND gate. This is the opposite to the AND gate, right? So likewise, the next gate is NOR gate. So before to the NOR gate, the IC number for the NAND gate is 7400. So you can remember that also. And the next gate is NOR gate. So like NAND is the combination of NOT plus AND, right? So likewise, NOR is the combination of OR plus NOT gate. So the operation is y is equal to a plus b the whole bar. That is what the operation of NOR gate. Okay, so you can see this is what the logical structure, and this is what the truth table for the NOR gate, the straight opposite version of OR gate, right? Okay, so the IC number for the NOR gate is 7402. Okay, so the next gate is EXOR gate. It is a special kind of gate. Okay, so generally the operation of the EXOR gate is y is equal to a EXOR b. Okay, so this is what the equation, that is the output equation of EXOR gate. So we can expand this equation like y is equal to a into b bar plus a bar into b. That is what the operation. Okay, so with the help of two inputs, we'll substitute this input and get the outputs with the help of this equation, right? Otherwise, one shortcut method will be there to find the output of the EXOR gate. So what is the shortcut method now? If the inputs are different like 0 1 and 1 0, okay, so if the inputs are different now, it will produce the output as 1. Okay, so you can see, so these are the different input. Okay, so you can see 0 and 1 and 1 and 0, so that means it will produce the output as 1. If the input are same, that is 0 0 and 1 1 now, it will give output as 0. Okay, different inputs it will give output as 1, and same inputs it will give output as 0, right? So that is what EXOR gate, right? I hope you understand. So the IC number for the EXOR gate is 7486. Here I'm just mentioning. Okay, so the last gate is EXNOR gate. So it is the combination of EXOR plus NOT gate, right? So like NAND and NOR, it is the combination of EXOR plus NOT gate. So it will produce a straight opposite function to the EXOR gate. That is, it will give 1 for the same inputs, right? For 0 0 and 1 1 it will produce 1. Okay, same input na it will give 1, and different inputs like 0 1 and 1 0 na it will produce 0. Okay, straight opposite to the EXOR gate, right? Okay, this is what the logical structure for the EXOR gate. And the output equation of the EXOR gate is very simple. Y is equal to a EXOR b. Otherwise, with an expansion is like y is equal to a into b plus a bar into b bar. So this is what the output equation of EXOR gate, right? I hope you understand that. So next we are going to discuss about the logical function implementation with the help of logic gates. So we'll see. See, you can see Boolean function implementation using logic gate. For example, here I am just mentioning one SOP function, that is summa product function, that is f is equal to a into b plus c into d bar plus b bar into c, right? So how to implement this logic function with the help of logic gate now, since it is very simple. You can see here, for this function we need one AND gate, and for this also we need one AND gate, and for this we need one AND gate, and two NOT gates are required, and for the whole function one OR gate is required. Okay, simply you can see a into b. Okay, so that means this will produce a into b. And what about the output here? C into d bar. Why d bar? Because there is a NOT gate here, right? So the next one is next AND gate will produce b bar into c because of this NOT gate, right? So totally we will combine this with the help of OR gate now. So the final output is f is equal to a into b plus c into d bar plus b bar into c. We can get it, right? So this is what the Boolean function implementation using logic gates in terms of SOP implementation. In case if it is POS implementation na, actually SOP implementation la and OR network will be used. That is, in the first side la we will use AND gate, and the second side la we will use OR gate. Okay. If it is POS implementation, OR and network will be used. Okay, so the first part la we are going to use OR gates, and the second part la we are going to use AND gate. Okay, so apart from that, the logical representation are very same only. I hope you understand today's content. So today we have discussed about the basics of logic gate, that is the representation and implementation. So there are different kind of logic gates were there. That is AND, OR, NOT, NAND, NOR, and EXOR and EXNOR, right? Okay, thank you.